In this video, we will continue to talk about approximations, and we'll come up with another method that will actually allow us to demand a certain accuracy in our approximations. Let's start with the same exact problem as last time, approximating square root of 2, but now I demand that it has to be with a certain accuracy. First, I'm going to actually turn what I would like to approximate into a function to work with. So I start off with x being square root of 2, which is the thing that I'm after here. I'm going to square both sides in order to get rid of square roots. And then I'm going to move everything over to the left in order to get an equation. So this is now a polynomial equation where x being square root of 2 is actually a solution to this equation. Let's think about this graphically for a second. So if I were to now sketch the situation, what am I going to see? I have a graph of x squared minus 2, which is just a parabola shifted down 2 units. And now I see that my square root of 2 and the negative version of it is actually an x-intercept of this function. So x-intercepts are also called roots. They're also called zeros. But among other things, this is the thing that I'm trying to approximate. So notice that approximating square root of 2 has now become an equivalent problem to approximating a root or a solution to this equation. And graphically, that means approximating the x-intercept of this function. Okay, so this is what I just said. I would like to note here just the vocabulary. We use the words x-intercept or root or zero interchangeably, as they all mean the same thing. Now, if I would like to approximate a square root of 2 being the x-intercept of this function, again, the best idea we had last time was the fact that a function or a curve is very well approximated by its tangent line as long as I'm close to the point of interest. And it's the exact same idea that we're going to take through this method as well. Function is approximately equal to its tangent line near the point of tangency. And in particular, function's x-intercept, which in our case is square root of 2, is really well approximated by the tangent line's x-intercept, again, as long as I'm somewhat close to the point of tangency. So my function's x-intercept is square root of 2. So now all I have to do is come up with a tangent line whose x-intercept then will be an approximation for square root of 2. Okay, so this, we know how to construct tangent lines, and we should be able to find an x-intercept of a line. So this is going to be our next task. We're going to pick an initial point, a point at which to construct a tangent line at, somewhere close to square root of 2, find an equation of the tangent line at that point, and then find its x-intercept. Now, first thing I'm going to do, because this is very nicely visualized with the graph, I'm actually going to sketch the situation first. I need to pick a point close to square root of 2. Well, I know that 1 squared is 1 and 2 squared is 4, so root 2 is somewhere between 1 and 2. 1 seems to be a good point, so 1 will be my initial first point. And that, so here I'm going to pick x equals 1, and I'm going to call it x0. It's my 0th guess, 0th approximation. I haven't done anything for it yet. And what's going to happen graphically is I'm going to construct a tangent line to my parabola at this point, and then compute the x-intercept of this line. Notice that my x-intercept line right here is really, really close already to the x-intercept of my function, which is the square root of 2. So I can already see visually that my approximation is going to be a very good one right after one step. Okay, so let me remind you that my function is x squared minus 2. And now I need to find an equation of a tangent line to this function at point 1. So for that, I'm going to compute the derivative, and I need my derivative at 1. So I'm going to plug in 1, and then I'm going to take the already equation that we've already used several times and plug all of this information into there. Okay, so what do I have here? My slope, I've just computed to be 2. x naught I picked to be 1. And y naught is, of course, the x coordinate that corresponds, the y coordinate that corresponds to this x coordinate. So I can just plug in x naught equals 1 into my function to get the y value. The y value comes out in this case to be -1. Okay, so overall, the equation of my tangent line turns out to be y plus 1 equals 2x minus 1. So this is the equation of the entire tangent line that I have on the graph. I'm interested in its x-intercept. So in order to find x-intercept, I'm going to set y to be 0 and solve for x. So what do we get? 0 plus 1 is 2x minus 1. And solving for x will yield x being 1.5. The square root of 2 is approximately 1.412. So this indeed is a fairly close value. The other thing that the graph, much like in the linear approximation method, is very good at detecting is whether the produced value is over approximation or under approximation. In this case, I can see that my tangent line's x-intercept lies to the right of my function's x-intercept, which means that my approximation will be an over approximation. Now, this is the exact same number that we got with the linear approximation last time. So how is this method better? Well, this method's main strength is the fact that we can repeat this process again with this as our new value. Okay, so my initial guess was x equals 1, and my approximation produced the next best approximation, which is 1.5. I can now go through the exact same process, but instead of 1 as the initial value, use 1.5. The construction will look exactly the same, but with a new point, and will produce an even closer approximation. Okay, so in order for me to do that, I will introduce a slight notation here. I'm going to call this guy now x1, because it's my first actual approximation produced by the method. Okay, and that's the idea here, is that now I'm going to take my point x1 to be 1.5, and I'm going to construct the tangent line at 1.5, compute its x-intercept, and that's going to be my next approximation of square root of 2. So please pause the video here and go through the exact same process as on the last slide, but with 1.5 as your initial point. And then also try to sketch on the graph what you think that will result in. Okay, pause right now, come back for the answer. Now, this is what you should have gotten as the result. So my next approximation here is 1.4167. Now, the actual true value is 1.412. So this is already up to 2 decimal places accurate with the exact answer, or with the decimal expansion of the exact answer. That's fantastic news, because once again, we can repeat this process again and again to obtain whatever accuracy you want, as long as the decimal places get fixed. Once they get fixed, that's the accuracy already attained. Okay, now let's take a look at what actually happens on the graph in this case, right? So here is where I have my function x squared minus 2, and the little circle indicates the point I'm actually trying to approximate, which is square root of 2, which is the x-intercept of this graph, right? So the method says, the way that we started is I'm going to start at 1, and I'm going to construct a tangent line at 1. Here is the tangent line at 1. So I went up to the function, constructed a tangent line, and then the x-intercept of this line is going to be an approximation of the x-intercept of my function, which in this case is root 2. So you can see how the red line intersecting the x-axis is really close to the function's black curve intersecting the x-axis. And I can repeat this by taking the red line's x-intercept as my next guess. Okay, so the process never changes. Wherever I start, I go up to the function, draw a tangent line, compute its x-intercept. So let's look at the next iteration. There it is. So the next line was orange. So at 1.5, I went up to the graph, constructed the tangent line, and you can already see that the x-intercept of the tangent of the second tangent line is so close that I know I'm going to have to zoom in further in order to even see where they're different. There you go. See how close the orange line's x-intercept is to the graph itself? It's pretty amazing that we got so close within just 2 steps. If I do the next step, I'm going to do the same thing again. I'm going to take the orange line's x-intercept, go up to the function, construct a tangent line. And here, the green, the new tangent line that is green, is already indistinguishable from the graph again. So in order for me to even see where it is, I'm going to have to zoom in. There we go, way, way further in, right? So this is already accuracy to what it looks like 4 decimal places. Newton's method is extremely powerful. The method will approximate very quickly and very well, okay? So just to be sure that we understand what's happening here graphically, let me put this graph in here. Okay, so this is my approximation. And now I just want to, again, remind ourselves that this one was our initial approximation, x naught. We went up to the function, constructed a tangent line, and the tangent line's intercept was 1.5, which was our next approximation, x1. We then did this again, and this is what this slide is doing. So then we went up to the function again, constructed a tangent line, and that x-intercept is the next iteration, or what we would call x2. And you will keep going until you're satisfied with the accuracy that you're getting. So the general idea is that we will start with the value close to the root of the function, or the x-intercept. So this is the guy we're trying to approximate right here. We will construct a tangent line at our point of choice. We will find its x-intercept and then repeat the process, okay? So graphically, again, we will go up to the function here, construct a tangent line at this point. The x-intercept of that line is our next approximation. So let's call this one x1, and then we can do it again. So then using x1 as our point, now I go back up to the function, construct tangent line. My next approximation is going to be x2, and so on. And you can see how I'm getting closer and closer to my point of interest, which is the x-intercept of the function itself. This is what it looks like on a graph. Let's try to derive this algebraically, because we should be able to go through all of the steps in a more general setting than with particular values, and hopefully come up with a formula that we can just use over and over again. So I have to construct a tangent line at that point, and then I have to find the x-intercept. So the first 2 steps are to construct a tangent line using a familiar formula. X-intercept is to set y to be 0. And then we're going to have to solve for x. This is what I get as a solution for x here. Make sure you actually follow through the steps to see how they worked out. And you will notice that here I replaced my y naught with the function value of x naught, and I replaced m with the derivative of the function at x naught. This way, this entire expression contains only my initial point x naught, my function, and its derivative. So if you give me a function and a point, I'll be able to find the derivative, compute the function value and the derivative value at that point, plug everything into this equation, and get the next approximation. So again, because we will be iterating through this method, this is what we will be calling x1, but then we can repeat this process. So with x1 in mind, I can repeat this again, except for I will be plugging x1 into here, and the algorithm will produce x2, and so on. So in general, and what I'm going to write is the most general description of this method, we can write that xn plus 1, so starting with some xn like x3 or x4, I can produce the next value, xn plus 1, is the value, of xn minus f of xn over f prime of xn. And this is the formula that is known as Newton's method of approximation. For Newton's method, one can ask questions that are based on the graphical understanding of the method or algebraic understanding or carrying out of the algorithm. Let's take a look at the graphical question. So here's a function that I have. So clearly the curve intersects the x-axis in 3 different spots, A, B, and C. So these are the x-intercepts or the roots that I might want to approximate. And the question asks, if I start at this point P, which root am I going to approximate using Newton's method? So thinking back as how the tangent lines get constructed, let me go through the first one here. So starting with this point P, Newton's method goes up to the graph, finds a point on the curve, constructs a tangent line, and uses the tangent line's x-intercept as the approximation for the x-intercept of the function itself. Clearly, here, the tangent line's x-intercept is really, really close to b as the root, right here, the little point b. And so proceeding with iterations of the method will only bring me closer to root b. So in this case, it approximates root b. I leave the other two examples for you to go through using the exact same logic. The second part of this question asks more broadly, because I have three roots, what if I'm after a particular one? So for example, what if I want the method to approximate root a? Where am I picking the initial values from in order to guarantee that my method will come towards root a and, for example, not root b, like it did in this case? Okay, so here you have to think about how the tangent lines get constructed. So in order for me to approximate root a, it means that the tangent line that the method will build has to sort of point toward root a. So notice that if I do tangent lines here or anywhere here, they will point toward a. But once I'm past this hump, this peak, my tangent lines will now start pointing to the other side, and I will be approximating some other roots. So for the first part here, it looks like past this point is where the tangent lines will diverge from a. So to approximate root a, I have to be somewhere between, let's say, minus infinity and this point right here. So let's call it minus 1.6. Okay? Using similar logic, please think about what are the intervals for your choice of x naught that will land you near root b and near root c. Now, this is one of the key things about Newton's method, is the method doesn't care which root you're trying to approximate. The method will approximate the root that is somehow closest to your initial guess. So in general, sometimes Newton's method fails altogether. We will think about this algebraically and graphically as well. Let's take a look at this general formula that we derived for Newton's method. When is this going to be non-computable, or what can go wrong in this formula here? Well, the thing that go wrong usually involves denominators of some kind. So the thing here is that this thing on the bottom, the derivative at xn, cannot be 0. Because if it's 0, I'm dividing by 0, I will not be able to carry on the calculations. So this cannot be 0. So this means tangent line can't be horizontal. The other failures of the Newton's method are better explained using the actual graphs. So this is our first case. Let's actually just graph this situation. So if I'm trying to approximate some sort of a curve right here, and I pick my initial guess to correspond with the point on the graph where tangent line is horizontal, the next step in the method is to compute the x-intercept of this line. But it has no x-intercepts, so the algorithm will stall. This is one of the failures, the horizontal tangent line. The next failure would be an interesting situation like this one here, where I pick x naught, I go up to the function, construct myself a tangent line. Let's say something like this. Let's pretend it's tangent. This is my next approximation, and the method will repeat itself. So it will go up to the function, find a point, construct a tangent line. Well, that's unfortunate, because now what that means is the method will just get stuck in a cycle, right? It will alternate between these two values because that's where the tangent lines will always lead it. So sometimes the method can get stuck in a cycle. This is a 2-cycle. Newton's method can have cycles of any length. So you can come up with functions and initial guess that will lead you to a 5-cycle, 7-cycle, any choice of cycle. So this is the second way in which it can fail. And the last way in which it can fail is something like this. So again, let's try to actually construct a tangent line and see what happens here. So for this choice of x naught, I'm going to go up to the function, construct a tangent line, take my next x-intercept as the next approximation, go up to the function, construct a tangent line. Well, that's not looking very good because look, the x-intercept is actually at 0 here, but my guesses get further and further away from this, right? So this will be x2. Get further and further away from my actual function's x-intercept. So in this case, what happens is because the curve is so flat, the actual approximations will diverge to infinity. So remember that I mentioned already that Newton's method is very fast, which means that it will give you the desired accuracy, a very good accuracy, very high accuracy, after only a few iterations. But the failures and our graphical previous example do suggest that when you're picking an initial guess, you have to pick it close enough to the root that you're actually trying to approximate. And you also have to keep the shape of the curve in mind. Otherwise, you might get stuck in you might end up in one of these cases where the Newton's method actually is not able to proceed. We're going to do a side-by-side comparison of the two approximation methods that we've talked about so that we can really see their similarities and their differences. So first of all, we're going to approximate square root of 48. It's the similar kind of function that we worked with before for square root of 2, but for a different number. So for linear approximation, the very first step is the fact that we're going to be approximating the function y equals root x near x equals 48. So at x equals 48. So that is the function that I'm going to draw, and that is the function that I'm then going to analyze. So sketching a quick picture here, remember that square root is a sideways parabola. Whoops, it starts at 0. So sideways parabola like this. So the point that I'm interested in is 48, and then its y coordinate is square root of 48. Okay, so in the linear approximation, I need to construct a tangent line somewhere close to this point, and then compute the y value on that tangent line for x equals 48. Now, nice point will be near 48, where I will be able to, in fact, compute the function value exactly. So what point near 48 is there where I can compute the square root of as an actual number without having to use a calculator and without any kind of decimal approximation? Well, 49 is pretty close to 48, and square root of 49 is 7. So that is going to be my nice point of choice here. Now, I'm not drawing to scale because otherwise it would be way too small. So the method will say at 49, we're going to build ourselves a tangent line and then compute on that tangent line the point that corresponds to 48. And that is going to be our approximation. So this is going to be my approximation here, whereas the corresponding point on the actual curve is the exact value. Okay, so now pause the video here for a second and write down the equation of the tangent line to the curve root x at 49. And then plug in x equals 48 into it here. Okay, so this is what you should have gotten. Notice that again, we're using our general equation for the line, but in order for us to be able to plug things in, I also have to compute the derivative of my function at the point. So here's where I am using 49 as the point where I'm computing the equation of the line at. And only once I've done that, am I going to plug in x equals 48 in order to find the approximate y value. Okay, and so you should get something like this, 7 minus 1/14, which is approximately 6.92. Again, the graph here emphasizes the fact that the approximation that you've ended up with is an over approximation because this point lies above where the point on the function does. For Newton's method, the very first step is to take the corresponding value that you're trying to approximate and turn that into a function for whom this is the x-intercept. So I'm going to square both sides first of all, and then move everything over to one side. And now I've taken my value that I'm trying to approximate and turned it into a function f of x whose solution, whose x-intercept I'm actually interested in. So here, the graph is going to look completely different because now I'm sketching x squared minus 48, which is of course a parabola that is shifted by 48 units down. So something that looks like this. Let's pretend it's symmetric. This is minus 48, and then the two x-intercepts are square root of 48 and minus square root of 48. So remembering what we talked about earlier, I have to be able to pick the initial value, the initial guess, close enough to the root that I'm trying to approximate, or I might end up approximating something else. Okay, so here I have to think of a number close to root 48. It can be anything. Newton's method is where you would actually be able to use a calculator, but with only subtraction, addition, multiplication, and quotient, no taking actual square roots. So you could pick any decimal around root 48. I'm going to do the calculations by hand, so I'm going to try to pick the nicest number available. Root 49, which is 7, is pretty close to root 48, so this is going to be my initial guess here. So this is going to be root of 49, which is 7. So my initial value that I am choosing is going to be 7. Now, the method, again, graphically, constructs the tangent line to my graph at that point, and the x-intercept of that graph is the x1 value. So that's my next best approximation. Okay, now using the formula that we've derived, the formula claimed that x1 was x naught minus f of x naught over f prime of x naught. So notice too that here I'm also going to have to compute the derivative of my function. My function is x squared minus 48, so the derivative is just 2x. So then the next step is to actually plug in my value for x naught, which is 7. So the function will be 7 squared minus 48, and the derivative is 2x, so 2 times 7. Calculating that out, I see that I'm getting 7 minus 1/14, which is approximately 6.92. So notice that my last line of calculations in both of these methods is actually identical. Okay, so yes, they've ended up with the exact same approximation, but for linear approximation, you're done. There's no way to proceed. Linear approximation will only be able to produce one value, and that's it, you're done here. With Newton's method, this is the first value it produces, and I can feed this value through the algorithm again in order for me to get a better approximation of root of 48 still. So please take a look at these methods side by side so you can really see how the setups are quite different, even though the ultimate goal of approximation is the same.
While we're not going to rigorously discuss a very important result called intermediate value theorem, it makes sense to talk a little bit about it in this section because we can actually apply Newton's method to find roots of equations with any kind of precision that we want. Here, though, before we get to Newton's method, is a general question. We have an equation. It's a cubic equation. We are asked to show that it has a root. And then we're asked for something even more specific. We're asked to find an interval of length 1 containing that root. So length 1 meaning, like, for example, between 5 and 6. Okay, the interval is something like that. So what do we know about this equation? And maybe before even the equation, what do we know about this function? What kind of function is this? Well, it's a cubic polynomial. We don't know how to solve cubic polynomials. Actually, we do. There are cubic equation solvers, let's say, kind of like the quadratic formula, there's a cubic formula, but this is not something that is generally considered to be, let's say, common knowledge. It's certainly not easy enough formula to simply memorize. So we have a cubic function. How can we possibly talk about it having a root? What is it about a cubic function that we at least know so far? So let's call it f of x, just so that it has a name, and let's discuss it as a function all in itself. One thing we know about it is because it's a polynomial, It's continuous for all real numbers. And we also know a variety of properties about it. Specifically, because it's a cubic function, we know that for large values of x, it will behave like x cubed. So if I were to produce a sketch, a very rough sketch of this function, the first thing I would look at is the end behavior. Again, power analysis tells us that for large values of x, this function will behave like x cubed, which means that it's going to have an end on this side here, and then it's going to do something in the middle that's cubic-like, but also is affected by other terms, and then it's going to come up on the other side and continue the x cubed behavior on the other side. Now, this is actually already more information than you think that will actually help us. It's continuous for all real numbers. It has to start down here and it has to end up here. So somewhere in the middle, it has to cross the x-axis. We don't know how many times. Maybe it's going to cross once, maybe it's going to cross twice, maybe it's going to cross however many times we want. But for certain, to get from this end to this end, it has to cross the x-axis somewhere. And that somewhere is exactly where our function is going to be equal to 0 and therefore produce a root. So this is already enough to show that the equation actually has a root. Knowing that it starts on one side of the x-axis and it ends up on the other one means it has to cross somewhere in the middle. But here we're asked for something even more specific, an interval of length 1 containing that root. So what can we do here? Well, let's try to narrow down this behavior of below the x-axis and above the x-axis and try to see where such the crossing might actually occur. So for that, all we're going to have to do is compute some values. So here it's completely sort of guess and check. Let's compute f of 0 because it's easy. So if I plug in 0 in for x, I'm going to get a 3. So now what I actually know about my function is that at 0, the function is up at 3, right here. And then, so that's above the x-axis. So I know it has to end up here and then continue on to infinity. Where does it cross here that will connect me to the previous end? So let's, for example, compute f of -1. If I plug in -1 in here, what's going to happen? -1 cubed is -1, plus 3 times -1 is -3, and then plus 3. So altogether, I'm going to get a -1. So at -1, my function is down here at -1. Well, that's fantastic news because now I have to get from this point to this point, again, in a continuous manner that I know the cubic polynomial follows, so I know I'm going to cross the axis somewhere in between. So this alone gives us the conclusion that since f of x is continuous, this is very important. If it was discontinuous, it could actually jump over the x-axis. Its graph will cross x-axis between those 2 points, so between -1 and 0. Now, I know it will cross at least once, but I don't know whether or not it's going to cross over more than once, right? So my graph could look like this, or my graph could very well look like that, right? All I know is that a crossing occurs. I don't know how many crossings actually do occur. Maybe more than once, maybe exactly once. Okay. Now that I have narrowed down the region where the graph actually has to cross, and that's between 0 and 1, I can now apply Newton's method to actually find the better approximation of the root of this equation. So let's start off with what we had. My function was x cubed plus 3x plus 3. And I know that for Newton's method, in order to apply the formula, I need to calculate the derivative. So it's 3x squared plus 3. Okay, now I know, so let's say we know there is a root between -1 and 0. So that means that for my initial approximation, I can take any number between those two. So for initial approximation, or one of the numbers themselves. Take any number between. Now, generally, the easier number is easier to compute with. So the easiest number to compute with is, of course, 0. So that's what I'm going to do. We're going to take x naught, my initial approximation, to be 0. Now let's recall the Newton's method formula. So for the formula, we have that x of x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime of x sub n. So here is now how I am going to go through and compute the next best approximation. My x naught is 0, so this is the value I know. My n here will be first of all set to be 0, so that overall this formula then gives me the formula for x1. Okay, I'm in fact going to rewrite it like that. So it's x naught minus f of x naught divided by f prime of x naught. And now I'm going to actually plug in all of those things into here. So x naught itself is 0, so this is going to be 0. And then minus the function value at x naught, so at 0. So I have to look at what my function is at 0, plug zeros everywhere here. So altogether, you know what, I'm going to actually rewrite this. So 0 cubed plus 3 times 0 plus 3 all over. And then on the bottom here, I have the derivative at 0 because, again, that's my x naught. So my derivative right here at 0 will be 3 times 0 squared plus 3. If I do all of the arithmetic, I am going to end up with -1. So that means that my x1 value now is -1. But I'm asked to find x2, the second approximation. So I have to do this process all over again. Now, in finding x2, because the method is iterative, I'm not sure I said it better the second time, I'm going to have this formula here in terms of x1. So if n is 1, notice that this formula turns into x2, which is what I have here, but the right-hand side has all of the calculations in terms of x1. So x1 minus f of x1 divided by f prime of x1. Okay, and now, same as before, I'm just going to plug in -1 everywhere here and compute with it. So x1 itself is -1. And then I have f of x1, so this formula of x1. So -1 cubed plus 3 times -1 plus 3 all over f prime of x1. So 3 times -1 squared plus 3. Okay, and again, doing simple arithmetic here, I'm going to end up with the answer that is -0.8 and then 3 forever. Okay, so my first approximation is -1. My next approximation is -0.8333. And I can compute and keep going forever until I am satisfied with the level of precision on my root. Every time I will get 1 or 2 decimal places fixed as a number, and then the actual calculations will only get more and more precise afterwards. Okay, so this is how we can actually not only find where the root approximately is by applying continuity to a sketch, computing some values and justifying that the crossing has to occur, and then applying the actual Newton's method to better approximate that root within the known region. For the rest of this lecture, we're actually going to go through a couple of examples from the previous tests. So here is the graphical example from one of the tests. For each initial approximation, determine graphically what Newton's method would do, and perform at least 2 iterations of the method. Again, by now you have all the tools that are necessary for this, and this comes directly from one of the quizzes from the previous offerings of the course. So pause the video here and try this out for yourself. Okay, so all of these are actually x naughts, Now, one thing to be mindful of here is your justifications for what Newton's method would actually do in each case really depend on your sketch here, because this is a purely graphical example. So you have to be able to justify your steps, and my tangent lines might not be exactly the same as your tangent lines. But as long as you've drawn out the method properly and explained what your justification was, this should be fairly clear. Okay, so what the Newton's method does is it takes the initial approximation and goes down to the graph, okay? Now, once I'm down at the graph, I am going to sketch the tangent line to this graph. And this is where your tangent line might be different from my tangent line, as long as it looks tangent enough and as long as your labelings are proper. This is going to create no issues, okay? So here is where I've approximated my tangent line to be, and the point of intersection of the tangent line and the x-axis is going to be my next iteration of Newton's method, my next approximation, x1. And then I repeat the exact same process. So I go up to the graph, I draw the line tangent to the graph, something along those lines. Okay, maybe a little bit better, there we go. And the point where the line crosses the x-axis is the next approximation. Okay, it has to perform at least 2 iterations of the method. At least 2 meaning if you can see what the behavior is after 2, then that's fine. And if you don't, then carry on. So here, it's actually becoming very clear what's going to happen. I'm going to go up to the function again. I'm going to draw myself a tangent line again. I'm going to end up even further back into infinity. I'm going to go up to the function again. My tangent lines are getting less and less steep, more and more shallow on this end of the function. So it looks like my approximations will start running away towards infinity. So here we will say that this diverges towards negative infinity. And again, I'm only doing the sort of short answers here, whereas on the test, if you got one of these scenarios, it wouldn't get necessarily all 4, then you should explain where you're getting your answer from in full sentences. Let's see what happens here. X naught is equal to 4. So this is my x naught here. I go down to Newton's method, to the function to apply Newton's method, and then draw the tangent line, which in this case looks like I've managed to hit just the very bottom of this parabola-like portion of our function. And I can see that this tangent line is now horizontal, which means that it does not intersect the x-axis. So there's not going to be the x1. So no x-intercept means no x1 value, which means that the Newton's method in this case will fail. Okay, and similar type of justification for the other 2. So I start with my x naught here for 5. I go up to the function, or down to the function in this case. I draw myself a tangent line. The intersection with the x-axis is my next value. I go up to here, I draw the tangent line, and I can actually see that my next value of the intersection x2 is already extremely close to the root of this function right here. So in this case, my method actually approximates the root at x equals to 6. And the last one, 0. So if I start at 0 here, I go up to the function, I draw myself a tangent line, and I can see that my situation in this case is very similar to my situation in the very first case. For the next one, my x1 is going to be further into negatives, and my tangent lines are only going to get shallower and shallower, leading me further and further into the negative numbers, and therefore the same conclusion will hold, but faster. It diverges towards infinity. Okay, this is a graphical type of test question. This is a multiple choice test question preceded by a very similar one about the linear approximation. So here we're asked to estimate the value of cube root of 26, but not actually to go through the entire calculation, rather just pick what function we're going to use and what initial approximation we're going to use if we were to apply Newton's method. Again, because this is from the test. Take a minute, pause the video, and try to reason through this question to see how far you get. Okay, so before actually looking at the multiple choices, let's think about the function and the method we're going to apply. So for Newton's method, we're going to start, remember, with setting the x to be equal to the thing that we want to approximate, and then we're going to turn that expression into a polynomial. So I'm going to take both sides and raise them to the power of 3, which will result in x cubed equals 26. And then I'm going to move everything over to one side to create an actual equation that I can use for Newton's method. Okay, so my function here is x cubed minus 26, which is this function right here. Okay, next up, we need to figure out what would be a good initial approximation. So in Newton's method, I need to look at this equation and try to think about what number will be close to a solution. Okay, so let me write this down. What number is close to solution of this equation? X cubed minus 26 equals to 0. Okay, so well, let's say I plug in 1. 1 is not very close to a solution. My outcome is not going to be very close to 0. I plug in 2. That's 8 minus 26, not super well. What about 3? 3 cubed is 27. 27 minus 26 is 1, which is close to 0. So the number that is close to the solution is 3. X equals 3 is close to a solution. So that will be my choice for the initial condition here. Okay, so don't just treat a multiple choice question as you actually have to go through each multiple choice and pick the one. Maybe actually writing down what you would physically do by hand when picking a route to proceed is going to end up with a more direct approach here. Then we have the exact same question, but now we're asked to use linear approximation. And so this once again highlights the difference between the two approximation methods that we're working with. So remember that for linear approximation, what we're going to do is actually come up with a function that looks like the one that we want, and our actual number that we're approximating is going to be the number on the inside. So for the linear approximation, we start off with the function we're given. We don't turn it into a polynomial or anything like that. We're starting off with the function look and feel of the original, because all we're doing is constructing one tangent line towards it. And we're going to approximate it for x equals 26. Now, that means that I can right away actually pick which one of these functions will match mine, and that's the top one here. The next one, though, is I have to pick the nice number to actually construct a tangent line to this function at. Okay, so my nice number has to be a number that I can take a cube root of. What is the nice number, or a nice number? It's not like you have a unique choice here. A nice number so it has to have two conditions. Close to 26, where cube root of a nice number here, that's what makes it nice, is easy to calculate, or can be calculated exactly, is, let's say, known exactly. Okay, so let's try to think of numbers here. So we can do cube root of 1 is 1. The next cube is 8, so that cube root of 8 is 2. The next cube is 27, so that the cube root of 27 is actually 3. So 27, notice, is close to 26, and we can take cube root of it, which means that 27 is our nice number of choice. So notice the big difference between the previous slide, where the function was a polynomial and the initial approximation, the initial guess, was the solution of that equation, or something close to the solution to this equation that made it as close to 0 as possible. And in linear approximation, we choose the function as is, And for the nice number, we choose the number that we can actually compute this function at. Okay? While both of the methods do approximations, they do it very differently. So the next slide is actually asking you to once again do both methods at once, approximating that exact same cube root of 26. Because we did an example exactly like that earlier in the lecture, I'm not going to fill this in. Go through and do a side-by-side comparison of the two methods so you can see how we've justified the previous two slides, the answers in the previous two slides, and how the methods are quite different, though both approximation techniques.